Now, when y'all do your notebook check, it's going to be a very simple way to get points in the class. Just because when you write down the notes, like we're going to explore functions, you're going to find out, you're going to ask yourself, we want you to start remembering what is a function. So one of the things that we want y'all to do is write it down so you can start remembering the words of what is a function. And really what it is a relation. So when y'all take your first notebook quiz, one of the questions is going to be on there. They're going to ask you, what is a function? All you have to do is write this down, what you wrote down in your notes, to get full credit. You don't need to do anything else. Just write down what you've copied during class. And you're going to find out that a function actually exists inside a relation, and for which every x value in the domain is paired with at most one y value. Actually, that's the definition of a function itself. A relation is everything, the whole coordinate plane. And function notation that we're going to be used is f of x pronounced f of x and gives a y value when you plug in a particular x value. Now let me go ahead and I'll be passing back your quizzes in the meantime when you write this down. Now, if y'all are finished writing that down, let's go ahead and we'll move over to the next part of this, the next part of these notes. That has to do now with the actual a really formal definition of what is function notation. And you're going to find out that a graph, one of the things that how we find out if something's a vertical line test is a graph is a function if and only if every vertical line intersects the graph in at most one point. And I want you to write down the note. If a graph is a function, we'll have to find the domain, the intercepts, and identify the symmetry. Y'all excuse me for a second. Let me move this screen. All right, lovely. All right, looks like just a little bit closer down, so wait a little bit. All right. Now, I want to show you some examples of what is a vertical line test. And what ends up happening is that we have this idea. Now, you don't need to write the top part of this because you wrote that down. You can write down one of the graphs if you wanted to be very accurate. Now, we have this idea, and this idea is very important. It's very fundamental and something that we do, in that you'll find out that any x and y value is called a relation. So, like any ordered pair you could think about. So, if you could think about like like 1, 1, 0, 0, anything you see in the Cartesian plane is called a relation. So, using like a Venn diagram, I could go ahead and tell you we have a relation. So a relation could be any x and y. What ends up happening is that a function actually exists in there. Okay, not every relation is a function. Functions are like a subset of a relation. So they're particular. So like this right here, the circle is considered to be a relation, not a function. And the reason being is that it has more than, for every x, it has more than one y. You might be wondering, why is that so important? Actually, functions are essential in how we work. And just to give you an example, suppose you go to an ATM machine and you wanted to get $100 from this ATM machine. So you click at the button that says $100. Now, if your function worked something like this one here, and where you could produce two different outputs, Imagine that this function, or imagine this machine, this ATM machine, is programmed in where it's a gamble, and where you could get either $50 or $100. I think you would be kind of upset if you click $100, got charged for $100, and then only got $50 back, right? We would expect that if you click the $100, you're getting exactly back $100. Not according to these type. These are relational. A function, no matter where any x value you pick, any starting point, there's exactly only one y. That's the reason why we do the vertical line test. This one, the same thing. It fails because of here. It has a failure in the system. So that's the reason why functions are so important to what we do. Now let's go ahead and actually go back to our notes. Start talking about right here, restrictions on domains. This is something y'all experienced yesterday. Yesterday, when y'all were doing your quiz, you found out that if a rational function, a fraction, you can, or any kind of fraction, you cannot include any values that will make a denominator 0. And you're also going to find out if your function includes square roots, you cannot include x values that will make your expression on the square root negative. Okay, so go ahead and write that down. It's actually like more of the exciting part because it's our actual examples. Now, with the domain, what you're going to find out is that we can't have the other, kind of like the other situation. You know, when you all took your quiz, question 1, this part right here was making a very valuable point. You know how we all have a numerator and denominator? So we have a numerator and a denominator. Well, what this is saying that you cannot have this ever existing. This does not exist for us. And most people confuse it because you're accustomed to seeing this. This is what you're accustomed to seeing a lot of times. You know, it's not very often you get a fraction and you're asked to say, well, where does this fraction not exist at? This is okay. This is good. This is a concept that we have space, but we don't have anything in it. That's okay. We could deal with that. We could deal with the idea that we have space and nothing inside of it to occupy. What we can't deal with is the idea that we have something and not say that it has any space. That's what that's meaning. That is non-existent. We can't find that anywhere. We cannot find that there's an object and it doesn't occupy space. So that's the reason why this is an error and why we have to state it when we look at our functions. So this happens actually right over here. Now, this is why, like, we're going to give you functions like these, and this is where it becomes important to know how to factor and know exactly how to find the zeros, because this is a quadratic, it's a parabola in the denominator. And what's going to be essential for us to find out is that with most parabolas, they'll cross the x-axis in 2 points. So since they cross the axis in 2 points, it means that there's 2 locations in where it cannot exist. So like in this case, we have the idea that if I factor this, remember this is a perfect square, which means that the conjugate are going to be opposite of each other. One's going to be positive, the other one's going to be negative. And that's how it makes that's why you have no middle terms in it. So you have x plus 3, x minus 3. This exact example was one of the ones on the pre-cal review. It was one of the ones that showed up. So we have this idea where we factor, and then now we have the 5x on top. Now for those that were, when I graded a lot of yesterday's quizzes, I did notice a common answer. They would just tell me that is, sometimes they'll just say, oh, it's -4. It's not necessarily just the opposite of what the number is. You have to, sometimes when it's more than, like if it's going to be a fraction, Sometimes you have to set them equal to 0 to find out what the x value is. The one from yesterday was actually a two-step equation. So when I set both of these equal to 0, and I do the algebra behind it, I find out that at two locations it cannot exist, which is x negative 3 and x minus 3. Now, we're going to write the domain right now. So far, everything that I've been writing down has been set notation. And what set notation is, it's describing something using these brackets. This is called set notation, where I say the domain, and you all see this bracket right here? That's called set notation. So I'm going to say domain is all x values such that, now I'm going to make it a little simpler. All we're going to write down in the such that is what x can be. So like in this case, we're going to write down x cannot be negative 3 or positive 3. That's what I'm going to write down in set notation. Now, when you all go into upper level maths, they are going to expose you to something else. Sometimes they're going to require you to say, what is x an element of? Now we're assuming, and this is what I need to make sure y'all you understand for the rest of the time I'm working this. We're assuming that x is an element of all real numbers. Sometimes they put that in there in the set notation to make it clear, because at times mathematicians will change it and say x is an element of the natural numbers, x is an element of just something different. But in our purposes, for just this class, we're going to assume this. We're going to assume that x is an element of all real numbers, so I'm not going to go ahead and put that in there. But it's one of the things you should know. This is called set notation. Now, I could also describe this with interval notation, more complicated. Actually, I would say that I'll talk about interval notation down here, because one of the things you're going to find out, like for this value right here, we found out that square roots cannot be negative numbers. And the reason why is because if you, like let's say that you get a negative 1 and try to do the square root, we move into imaginary. So if you notice this equation right here, this equation is going to be solved by finding out what is bigger than 0 on it. And I think most of y'all can see it. You can say, okay, at negative 5, that's when anything that is bigger than negative 5 is we'll make that like, or less than negative 5, better said, anything less than negative 5. So like if I put negative 6 in here, negative 6, negative 7, so on, so on, so on. If that goes in here, it's going to make an imaginary number. And we can't have that. So we have to tell it that it's everything that's greater than this point. That's the reason I wrote this equation. X has to be bigger than x plus 5. So when we find out the exact amount by doing the algebra, we'll find out that x is everything bigger than 5. Now, x could also include 5, because if I put 5 in there, negative 5, if I place that in there, it makes 0. I can find the square root of 0. It's 0. That exists. What does not exist is anything that will make it negative. So when I write the domain on this one, write the domain. The domain on this is set notation again. X such that, let's see what this is. All right, so now, going back to this. Okay, so we're going to put x, and this is set notation again, such that x is every number that's greater than 5. So now I have my domain listed. Now now this is interval notation. I mean set notation. So we still are dealing with sets, and they're defined by the brackets. So set notation. Yes. Yeah. Oh, actually, negative 5. Sorry about that. Thank you for pointing that out. Yes, you're right. I put down 5 and carried the negative. Now, let's talk about interval notation. Interval notation is one that some of y'all have seen already. Interval notation actually deals with inclusions. So like when you write interval notation, it's writing the same thing. Now there's two things with the interval notation. Like this means a bracket means included. Let me go ahead and fix this. A bracket means included. So when I write down a bracket, this is included. So I'm going to include negative 5. and then I'm going to say it goes all the way to infinity. Okay, so this is called interval notation. It's a way to describe the domain by describing the range of values. It's the same. It's very similar to the set notation, just in the fact that it's written differently. So you have to know that eventually you're going to be exposed to interval notation as well. So you're going to know that as well. Let's go ahead and actually have you write down just one more page of notes. Well, actually, I'll have you finish writing that down. And then we'll do one more page. And then after that, I think we're going to get started and look at the reviews and everything else that you've done so far. So this is what we're going to get into, and especially tomorrow, operations of functions. And what we're going to do with these functions is we're going to be able to add them, subtract them, multiply them, and divide functions. And when we do this, we have to identify new domains for your functions and carry existing domains, because it's like a grandfather clause. I don't know how many of you have ever heard about a grandfather clause. There's certain things they call grandfather, which means that it still contains those old rules, and they move over to, even though like some of y'all might have grandfather cell phone plans. I think that's probably the most common one you're going to run into, and where you'll have like an old cell phone plan that now gets carried over because you originally signed up with them like that. So something like that. You carry the past domains into the new domains. That's the best way to describe it. Oh, you know what? Let me go ahead.